everyone, let's start off where we stopped in our last video, which was the spin quantum number. So my goal today is let's talk about spin quantum number and then also just go through the slides that had those 3 electron configuration rules, because we did allude to those today in class. And last thing that I want to introduce before we stop this video is something called photoelectron spectroscopy. And then on Monday, we're going to spend the whole bell talking about the photoelectron spectroscopy, understand different kinds of AP level questions that you may see that has to do with PES. And I also want to spend just a little bit more time with quantum numbers to make sure that we are good and solidified on that knowledge, okay? Now, if you would also do me another favor, because I know that Tuesday is redo day, if you, after you watch the video, while you're on the blog, can you post a comment for me that tells me just yes or no if you are going to redo day or if you're not going? So if you are, post yes. If you're not, post no. Just so that way I know how to plan for Tuesday and then kind of the rest of the week, because it may throw off some stuff that we're doing. So if you would do that, that would be awesome. So thank you. Okay, let's go back to spin quantum number. Actually, let's just review all of our quantum numbers quickly. We know that principal quantum number is the energy level. We'll designate that with an N. We know that angular momentum quantum number is denoted with an L, and that ultimately just means the shape of the orbital. So if it's S, then I know it's spherical in shape. If it's P, it's a dumbbell in shape. If it's D, it's cloverleaf in shape, and F is going to be just some random thing because we don't know what they look like. In terms of values for L, if L is equal to 0, it's S, L equals 1, it's P, L equals 2, it's D, L equals 3, it's F. The third quantum number is called magnetic quantum number, which just tells me orientation. So I think that the orientation may be a little clearer after you looked at the worksheet that you got on Friday. And especially thinking about the p orbital in the x direction, in the y direction, and in the z direction. So I know that I have orbitals that align with those axes because for the magnetic quantum number, I know that it's going to be the positive and negative integers of whatever number my L value is. So let's say I have an L of 1, which is the p orbital. I should have a -1, a 0, or a +1 for my possible values of the orientation. So I have 3 different orientations that the p orbital could take, and we do know that using instrumentation, and that's along the x, the y, or the z axes, okay? The fourth quantum number is spin quantum number, and we alluded to this last time, but ultimately what happened was that scientists studied Bohr's idea of these line spectra, and then Balmer's idea of these line spectra, and they noticed that lines that were originally thought to maybe just be single lines, these single wavelengths, were actually really closely spaced pairs. So I may not have just had one line coming off, maybe I had a couple of different lines that I saw there. So this meant that there were twice as many energy levels as maybe there were supposed to be. But really, we just found that electrons that occupy orbitals have different spins. So again, when we look at this, ultimately what we thought was that if we have this beam, sorry guys, if I have this beam of light and then I allow it to go through this slit, which is having the beam of light to just go through the slit is really just making sure that when it goes through the magnetic field, it's a nice, more uniform straight line. So I have this beam of atoms going through the slit, and then as soon as it enters into that magnetic field, the magnetic field is going to interact with that electron spin. So ultimately this magnet splits the beam in 2. This is what we observed. So then once that beam is split into 2, it shows that it's deflected one way, and then the other one is going to deflect towards the opposite way. So because of that, we just say that the electrons have equal in magnitude, but opposite in direction in terms of their spin. Okay, so the spin of an electron just pretty much helps us kind of define its magnetic field. And remember, we said that it will be a positive 1/2 or a negative 1/2. Okay, so the next slide is just going along the same thing. It kind of helped us as scientists to think about an electron as just behaving like a little sphere that rotates or spins around its own axis, which is, I mean, if we think about it in terms of our planet, it kind of helps that way too. So I have these electrons, and the way that they're oriented, if this is an axis here, it's going to spin either counterclockwise or clockwise. Then I see that axis directed in a different direction on the other one. So we will allow the values to be a positive 1/2 or a negative 1/2. This brought up one of the first electron configuration rules that we have, in that no two electrons in the same atom can have exactly the same energy. Just meaning that I'm not going to be able to find a positive 1/2 electron spin and another positive 1/2 electron spin occupying in that same orbital. So it says, therefore, no two electrons in the same atom can have an identical set of quantum numbers. So every electron is going to have its own set of quantum numbers. Because there are only two possible values, an orbital can hold a maximum of 2 electrons. So I could have a positive 1/2 or a negative 1/2, and they have to have opposite spins. So Pauli exclusion principle is really stating that an orbital can hold a maximum of 2 electrons, and those electrons must have opposite spins. Okay, we already know how to write electron configurations, so just as a refresher, there's 3 different components in an electron configuration. I have the number denoting the energy level, which will go in front, so that's the principal quantum number. I have the letter that denotes the type of orbital, that's the angular momentum quantum number. And then I have how many electrons that we have, so a superscript denoting the number of electrons in those orbitals. When we draw orbital diagrams, you did a little bit of this on your summer assignment. So when I draw an orbital diagram, ultimately we're going to represent an orbital by drawing a box. So one box represents one orbital. So if I think about the one that only would have one orbital, that would be the S, because it can only hold at max 2 electrons. You know that the S orbital can hold only 2 electrons. So if this were lithium, I see that lithium's electron configuration is 1s2, 2s1. So I'm going to draw a box for the 1s orbital, I'm going to draw a box for the 2s orbital, and then I need to represent the electrons. So we are going to represent the electrons as half arrows, and that's going to show me the positive 1/2 spin or the negative 1/2 spin. So if it's a positive 1/2, I'm going to draw the half arrow up. If it's a negative 1/2, I'm going to draw the half arrow down. But this is Pauli exclusion principle here, me showing that I have a half arrow, that one is directed up and one is directed down, okay? So ultimately, Hund's rule is just stating that I need to make sure that each orbital I need to make sure that an electron fills up each orbital first before I can start pairing those electrons. So it says for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. So I'm going to have the positive 1/2 first, and